Dr. Marshall N. Rosenbluth, a senior research advisor at the laboratory, and one of the world's foremost theoreticians in this field. Theorists associated with the program of Texas power companies and General Atomic have made many important contributions to the fundamental plasma theory, which serves as a basis for present-day fusion research throughout the world. Following early attempts to heat plasma in a bottle, General Atomic scientists pioneered a bold new concept called the gunshot method. In this new method, the plasma is created outside the magnetic bottle and shot into it from plasma guns at speeds up to 1,000,000 miles per hour. The plasma is stopped in full flight by the magnetic walls, converting its tremendous energy into heat of over 1,000,000 degrees. The magnetic bottle used in this experiment is called the mirror. The device takes its name mirror from the fact that the ends of its magnetic container are pinched to give the bottle a neck at each end. When the plasma is shot into the bottle, the pinched ends act as a mirror, reflecting the plasma back into the center, reducing the amount of plasma that escapes. Magnetic bottles in use today are of several different kinds. This one, quite different from the mirror, is called the multipole and was invented under the program of the Texas power companies and General Atomic. It represents an important new approach to achieving plasma stability. This model of the multipole shows features of its design hidden by the machine itself. 4 current-carrying rods produce the magnetic bottle. They are arranged in a circle so that the bottle formed will be a closed loop without any ends for the plasma to leak out. A gun fires the plasma through the magnetic wall into the bottle. The magnetic field lines arc out between the rods to form a bottle which increases in strength in every direction away from the plasma. This configuration is what gives the bottle its remarkable stability. The magnetic bottle is formed by discharging electrical energy from these banks of giant capacitors. For a microsecond, they can discharge more electrical power than is created by the largest power plant in the world. In an actual experiment, a plasma gun injects the plasma through the magnetic field into a bottle at 300 miles per second. Plasma temperatures achieved during this test were over 1,000,000 degrees. The scientists experimenting with the multipole are adding volumes of precise scientific data to our knowledge of plasma behavior, bringing us ever closer to our goal of achieving a sustained fusion reaction on Earth. Concurrent with their efforts to contain, heat, and fuse atomic nuclei in magnetic bottles, researchers on the program are isolating various facets of the problem for special study. One group of scientists is concerned specifically with plasma guns. They are improving the injection velocities and the purity of the injected plasmas. A Others are gaining advanced scientific knowledge concerning plasma behavior with this device called an anomalous diffusion machine. The device produces a narrow, constant jet of glowing plasma in a magnetic field, which allows scientists to study the mixing of plasmas with magnetic walls. In this experiment, the scientists are developing a technique to rid plasma of heavy ion impurities. A gun fires a charge of intensely hot plasma into a curved magnetic pipe. The experiment is designed to solve the problem of transporting high-purity plasmas from guns to bottles. Fusion research at the University of Texas and Texas A&M includes investigations of plasma injected into and across magnetic fields, as well as plasma analysis using an intense, coherent beam of light from a large laboratory laser. Today, the scientists working on controlled fusion research find themselves in much the same position as a man who has discovered a locked treasure chest crammed with immense riches. He cannot open it because he has not yet found the key. This is Dr. Edward C. Kreutz, General Atomic Vice President with overall responsibility for research and development. Dr. Kreutz, what is the present status of research in controlled fusion?
We are making steady progress in our understanding of the real problems of plasma. There have been waves of optimism and of pessimism, as is true in any field of research. But today I'm happy to report the enthusiasm of all workers in the field is higher than ever before.
We understand that research in plasma is providing us with new knowledge in other important fields.
Yes, and this is not surprising, since most of the universe exists in the plasma state. As we learn more about the physics of plasma, we are learning a great deal more about the universe.
Specifically, what about the possibility of controlled fusion as a source of electrical power?
Let's be optimistic and look beyond the immediate problems of understanding the physics, and then beyond the problem of engineering suitable devices. And let us further assume that we can ultimately build a plant that can convert fusion energy into electrical energy economically. Exciting possibilities are opened up. All those uses of electrical power which have been dreamt of, but which have not been practical as yet, will be possible. Power for pumping water to the deserts, for changing the weather, and even for propelling man and his scientific equipment to other planets. Indeed, for doing most of the mechanical work of civilization, as well as for heating and cooling our cities. The incredibly large quantities of deuterium in the oceans can, in principle, provide the fuel supply to fulfill man's unlimited dreams.
Power that lies waiting for us in the oceans of the earth. Enough energy in a child's pail of water to heat, light, and cool a home for a year. Power for our world of tomorrow, from the energy process of the sun and the stars. The rewards of success could benefit all humanity. This is the challenge that has been accepted by the companies of the Texas Atomic Energy Research Foundation in what may be the most important peacetime scientific effort ever undertaken.